Solving exponential equations can be easier if you identify what type of an exponential equation you're solving. Now there's some general types. One is if I have a number base to a power is equal to a number. Another is if I can rewrite it so that both sides of the equation are to the same base, to a power. And then the other one that's just a little bit messier is if you have exponential expressions on both sides of the equal sign, but the bases aren't equal, nor can you make them equal. So in this video, I'm going to show you each of these cases and how you would go about to solve them. The first one here is to solve the exponential equation 5 times e to the x is equal to 30. So here I have a number base to a letter power, and I'm trying to solve for that variable, but the variable is caught up in the exponent. So to do this, the first thing I want to do is to make sure that I get the expression that's the number base to the power on one side of the equal sign and everything else on the other side. So I'm going to divide both sides by 5 first to get e to the x is equal to 6. Now again, I'm solving for x, and x is caught up in the exponent. Now there aren't logarithms involved in this equation so far, but if I use the logarithm that matches the base of the exponential expression, then I have inverse functions and I can work with that property to then get at the variable x. Now this is base e. The logarithm that's base e is the natural log. So I'm going to take the natural log of both sides. What I do new to one side of the equation, I'm going to do new to the other. And since the logarithm is a one-to-one function, I can take the log of both sides and it'll still be an equation with an equivalent solution. Now here I could go two different ways. One way is that now that I have a natural log of an expression to a power, I can use properties of logarithms and bring that power down. So that's x times the natural log of e is equal to the natural log of 6. But the natural log of e is what exponent would you put on the base of e to get e? Because remember, natural log is base e. Well, that's the exponent 1. So the natural log of e is just the number 1. And x times 1 is just going to be x. So x equals the natural log of 6 is the solution to that equation. Let's look at the next one, part B. Here, I have 8 to the 2x plus 1 is equal to 4 to the x minus 7. I want to solve for x, and x is caught up in the exponent, and that's why we call it an exponential equation. Well, I noticed that 8 comes from 2 cubed, and 4 comes from 2 squared. So I could write both of these sides of the equation as the same base. So we're going to replace 8 as 2 cubed, but that 8 is raised to the 2x plus 1 power. And I'm going to rewrite 4 as 2 squared, but that 4 is raised to the x minus 7 power. Now we have to remember something about exponents and properties of exponents. When I have an exponential expression to yet another power, I keep the base and multiply the exponents. So you can kind of think back to like when you have a to the 3rd raised to the 4th power, I keep the base and multiply the exponents. So that gives me a to the 12th power. So I have the same scenario here. So I have my base of 2. Now 3 multiplied to 2x plus 1 is going to be 3 times 2x is 6x plus 3 times 1 is 3. On the right hand side, I have that same property. So when I have an exponential expression raised to yet another power, I keep the base and multiply the exponents. So that will be 2 to the 2x minus 14. Okay, now that we have this equation and I have the same base on both sides, and exponentials are one-to-one functions, if the if I have an equivalency of the same base to powers and they're equal to each other, then the powers have to be equal to each other. So 6x plus 3 has to equal 2x minus 14. And now I can just solve this equation for x. So we'll subtract 2x from both sides. That gives me 4x plus 3 is equal to negative 14. And then finish solving the rest of it. We will subtract 3 from both sides. I get 4x is equal to negative 17. And then divide both sides by 4. X is equal to negative 17 fourths. Okay, now the last one here is where I have exponential expressions on both sides, but the bases don't match, nor can I rewrite them as the same base to a power. So here I'm just going to have to take a logarithm of both sides to try to get that exponent down. And I can't really do a specific base that would help me with the inverse function idea. So we can do either the natural log of both sides or the common log of both sides. It really doesn't matter. So let's go ahead and do the common log of both sides. So we'll go log base 10 of 3 to the 4x minus 1 is equal to log base 10 of 2 to the x plus 3. Now that I have logarithms in there, and again, we took the logarithms of both sides. We had to be fair to both sides. So now I can bring the exponents down so that 4x minus 1 gets multiplied by the log of 3 is equal to the x plus 3 is multiplied to the log of 2. And now remember, we're solving for x. So to solve this for x, we're going to have to get rid of the parentheses, get all the terms with x on one side, all the terms without x to the other side, factor out the x, and then finally solve for it. So when I distribute the log 3, remember, log 3 is a number, so you have to keep that intact. Log 2 is a number, so you have to keep that intact. So when I distribute it, I have 4x log 3, and then negative 1 times log 3 is minus a log 3, is equal to x log 2 plus 3 log 2. Now here's my equal sign. This term has an x, but this term doesn't. There's my equal sign. This term has an x, but that term doesn't. So I'm going to get all the x terms on one side, all the not x terms on the other side. So we're going to subtract an x log 2 from both sides and then add a log 3 to both sides. So I have 4x log 3 minus x log 2 is equal to log 3 plus 3 log 2. Now I can factor out a common factor of x. And then to solve for x, since it's x times this expression is equal to that other side, we're just going to divide both sides by 4 log 3 minus log 2. So x is equal to log 3 plus 3 log 2 divided by 4 log 3 minus log 2.